Sir, welcome you on board. Can you able to hear us, Professor?
Yeah. Now is it audible from my side?
Yes, yes, Professor.
Okay.
Just we had earlier previous session we had Dr. Avais Ahmed with us. Just he left the meeting.
Okay,
Just he
sir.
finished the presentation, Professor. Professor, can we have 2 minutes break and then can we start?
Yeah, sure.
Yeah, Professor. Thank you.
Thank you.
So, participants, we have 2 minutes break and we'll start by now. It's time is 3:15. We'll start by 3:17. Prabakaran, sir.
Yeah, sir.
How are you, sir?
Yeah,
How the
good,
things
sir.
are going on in
Yeah,
Korea?
everything is going fine here. How about that?
It's going good here also, sir.
Nice to see you after a long time, sir.
Yes, sir.
Maybe
Yes,
around
sir.
2 to 3 years, right?
Yeah,
After
yeah,
2
sir.
to 3
What
years.
is the time there, sir?
So now time is around 6:48 here. 3 hours 30 minutes earlier.
Evening.
But yeah, evening 3.
Okay. Evening 6. Okay.
Yes, sir.
That's why I scheduled your session Saturday because all other days we had session between 6 to 9.
Oh,
It
it's
would be
too
very
late for
difficult.
me. Yeah, yes, sir.
Yeah, that's why we scheduled your session on Saturday in
Yeah.
the middle of first and third session.
Okay, sir.
So, can we start, sir?
Yeah, sir. No problem. We can start.
Sir, are you there? Can we start, sir? Shivakumar, sir, are you there, sir? Shivakumar, sir?
Yeah, sir, available, sir.
Yes, sir.
Good evening,
Prabakaran, sir, will go for a formal.
Oh, yeah,
Yeah,
sir.
Shivakumar, sir. Okay, sir, you please start. Now I request
Good evening, everyone.
Professor Shivakumar. Yeah, please, sir. Please go ahead, please.
Prabakaran, sir. Good evening, sir.
Good evening, sir.
Good evening to everyone. I am Mr. Sivakumar, Assistant Professor in the Department of Mechanical Engineering at Adishankara Deemed Tube University, Godur, Andhra Pradesh. It gives me great pleasure to introduce our distinguished resource person for his this session, Dr. Rajendran Prabakaran, sir. He is currently working as international research professor at Thermal Management and Energy Systems Lab, School of Mechanical Engineering Yangonam University, Gangtek, Republic of Korea. He's obtained his PhD in refrigeration and air conditioning systems from Anna University, Chennai. For the past 15 years, he has been working in the field of HVAC systems, alternative refrigerants, solar refrigeration and air conditioning systems, battery thermal management systems, etc. And he is published more than 90 research papers in international journals focusing on HVAC systems, automobile air conditioning systems, alternative refrigerants, phase change nanocomposites, and thermal management of batteries, etc. On behalf of the organizers and all participants of the sessions, I extend a very warm welcome to you, sir, Prabakaran sir.
Thank you so much, Shivakumar sir.
With these words, I now hand out to this session to our esteemed resource person, Rajendran Prabakaran sir. Sir, take sir.
Thank you so much, Shivakumar sir.
Thank you, sir.
Good evening to all esteemed faculty members and participants. Myself, I am Dr. Rajendran Prabakaran. It is indeed my privilege to deliver this lecture as a part of ATAL FDP on smart transition for a greener tomorrow, innovations in energy and sustainability. So herewith, I'll start to share my presentation. Is it visible?
Yes, sir, visible, sir.
Yeah, fine. The focus of today's lecture is on eco-friendly refrigerant and sustainable cooling system in buildings. This theme is a paramount important, giving the dual pressures on rising global cooling demand and the urgent need to mitigate the climate changes. Once upon, cooling is a luxury, but now it's become an essential component of modern life and economic activities. However, its associated energy consumption and environmental impacts poses serious challenges. Therefore, sustainable HVAC systems and the adoption of low GWP refrigerants are not just a technical consideration, but it's a crucial component of a global sustainability agenda. So the purpose of this faculty development program on this particular topic is to create an awareness and knowledge on the eco-friendly refrigerants and to equip faculty members with updated concepts and to promote innovations and best practices for reducing the environmental impact. So let's start with global energy productions, like energy consumptions. Globally, the building sectors are responsible for approximately 40% of total global energy, in which HVAC systems are being as a major contributors. Traditional refrigerants like CFCs, HCFCs, and HFCs have enabled rapid spread of cooling technologies with efficient performance, but at a significant environmental cost. So we can see from this slide, you can see the challenge of sustainable cooling become more acute in rapid developing economics like in India. We can see this highlighted box. The projection indicates that by 2027, the energy demand for building cooling in India will be approximately 57% of total cooling demand, especially for building cooling, followed by the refrigerant component, refrigerators and other associated components at nearly about 25%. And this demand will increasingly significant and increases more energy stress on the grids and sustainably increases the refrigerant consumptions. However, the projection demonstrated that adaptation of available strategies and new advancements, this aggregated growth in energy demand can be curtailed by 17%, and the emission might be reduced by 20%. So all these statistics underscores the urgent need for policy intervention and the deployment of eco-friendly refrigerant solutions. So at the core of this discussion as always lies on the refrigerant itself. Everyone knows that a refrigerant is a working fluid in the refrigeration cycle that absorbs heat during the evaporation and releases it during the condensation. It has a role indispensable in maintaining the thermal comfort, refrigeration, and air quality in the buildings. However, it has major concerns on the environmental aspects. So such aspects are global warming potentials and ozone depletion potentials. Like refrigerants, like earlier refrigerant, like CFCs and HFCs releases chlorine and bromine compounds that could damage the ozone layer. On the other hand, HFCs, it has zero ODP, but it potent greenhouse gases that traps the thousands of heat more effective than carbon dioxide. Due to that, the global temperature will rise. These consequences are evident in the form of climatic change and increasing greenhouse gas emissions and higher energy intensity in building sector. Thus, there is a huge need, and the transition to low GWP and energy efficient refrigerant is indispensable if we are to achieve net zero energy building concepts, reduce carbon footprints, and improve indoor environments. So these are all the basic classifications of refrigerant based on the chemical compositions. Under the single component refrigerant, it can be categorized as natural, in which ammonia, water, and other refrigerants are there, and hydrocarbon based refrigerant, which categorize under further R600A isobutane and R290 propane. And the older one, that red color indicates it's all synthetic refrigerants, which has earlier it was used in all kind of systems like chlorofluorocarbon R22 and R12, hydrochlorofluorocarbon R22, hydrofluorocarbon R134A, and recently, I think a few years back, they introduced another refrigerant based on hydrofluoroolefins. The difference between the HFCs and HFOs is that double bond of carbons, which makes an unsaturated molecules and which is less stable in the ambient and also has ultra low GWP as compared to HFC refrigerant. On the other hand, mixing of one component of refrigerant with the another one, like mixing of HC with CFCs, or mixing of HFCs and HFOs, mixing of natural refrigerant and other synthetic refrigerants. It can be categorized into two types: zeotropic and azeotropic. Azeotropic means the mixtures, like different components it has in a mixture, all components might have a similar boiling point. There will be a no temperature glide, and it cannot be separated during condensation and evaporation. Usually, these refrigerants are designated by R500 series. On the other hand, zeotropic mixtures might have different boiling point among the components and shows very high temperature glide. These refrigerants are designated by R400 series. So history of refrigerant and amendments. Due to the environmental concern, in 1987, Montreal Protocol initiated the phase out of ozone depletion refrigerant like CFCs R12. At that time, the transition completely moved towards HCFCs and HFCs in commercial and automobile sectors. These refrigerants do not have ODP issues, but it has high GWP. Later years, in 1997, Kyoto Protocol was introduced because of increasing the global temperature issues. The major objective of that protocol is to reduce greenhouse gas emissions globally by the refrigerants. In that case, so what they introduced is they proposed to ban all the high GWP refrigerants in HVAC systems. So in latter part, in 2016, Kigali amendment to that particular Montreal Protocol, they have introduced a step-by-step reduction of these high GWP HCFCs and HFCs based on the different developing and underdeveloping countries. Based on that strategy, it was proposed, and around 2040, there should be no high GWP refrigerants in all kind of systems in India. So apart from these protocols, recently in European Union, they have introduced the PFAS regulations under restrictions under REACH regulations. This even reduced the indirect impact of the refrigerant. Like if we use HFOs, it has 0 ODP, very ultra low GWP. But when these refrigerant releases into the ambient, it will react with the ambient and it might form acidic rain because of its TFA formation. So these kind of protocols again pushed towards the natural refrigerant. Then Indian policies and institutional frameworks. So starting from Kigali Amendment to the Montreal Accord worldwide, in India, Indian Cooling Action Plan adjusts of this transition, and it has very long-term vision with a specific targets like a reduction in cooling demand of building sectors by 20 to 25% by 2038. Similarly, reduction in refrigerant demands by about 30% for the within the same period, and also reduction in cooling energy requirement by up to 40%. In addition to ICAP, other policies including ECBC standards and labeling programs and contributions from the professional organization like ISRE, BIS, and ICBC are all collectively supports this framework to the goal of energy efficiency and environmental protection. So next, criteria for refrigerant selections. Usually the refrigerant will be selected based on 3 aspects. One is thermophysical properties, environmental concerns, and safety concerns. The refrigerant should have good thermophysical properties, including high latent heat of phase change, low density, high vapor density, high thermal conductivity, low surface tension, and etc. On the other hand, it does not have ODP and lower GWP. So these two are for the system performance and environmental consequences. And the third one is safety concern. So based on the ASHRAE 32 classification, you can see from this figure, there are 6 classifications. Now recently they added 2 more. So 8 classifications based on the toxicity and flammability. So it is always expected to have a lower toxicity and no flammability. But you can see from this right side tables, there are different refrigerants starting from the HFC like R134A, R152A, and from the HFO side R1234YF, ZT, and the last one is hydrocarbon refrigerant. You can see from this, HFCs has manageable good performance, but on the other hand, it has very high GWP. But HFOs, it has low GWP, but its thermophysical properties are somewhat lesser than HFC refrigerants. And also it has TFO issues. And the last one, you can see propane, like propane and isobutane from the hydrocarbons. Both these refrigerants are have excellent thermophysical properties, but it is highly flammable. And like in ammonia also, it has an excellent thermophysical properties and it does not have flammability, but on the other hand, it is highly toxic in nature. So from this point of view, we can see that there will be no single refrigerant satisfies all these criteria, which necessitate a trade-off between thermophysical properties, environmental concerns, and safety aspects. So usually the refrigerant performance has been analyzed through step-by-step procedure. First, the refrigerant will be selected based on the thermophysical properties, and then theoretical analysis using thermodynamic calculations. And after that one, we will proceed for usually a test bench studies in the laboratory level, followed by TEVI and LCCP analysis regarding the environmental concerns. After all, the real-time testing and implementation will be carried out. So these are all the low GWP refrigerant replacements and expectations. Like under low GWP HFCs, we can see that R32 and R152A are the frontliner. And in HFOs, R1234ZT, R1223 and R1234OF are the frontliners. And the natural refrigerants and HCs R290 and R717 are the frontliners in the building sectors. But R744, it's a CO2 refrigerant. It is usually not, like, how can I say, it is usually perform well under the heating condition rather than the cooling conditions, because and also it has transcritical and subcritical cycles compared to other refrigerant because of its very low critical temperature. And some other refrigerant mixers also listed. From all these refrigerant mixers, the expectation is it should give either comparable or increased cooling performance as compared to the existing refrigerant, and also should have improved COP at retrofitted conditions. Retrofitted condition indicates that there will be no changes in the system component level side, only the change of refrigerant from the old one to the new one. And if it is a new system, it should matches with the overall existing system performance, and it should consume less power and should have good material compatibility and emits less CO2. So these are all the real expectations from the various alternate refrigerants. So now let's move into the some research studies on low GWP refrigerants specific to the air conditioning applications. Let's start with the theoretical analysis. This work is focused to identify the future refrigerants for split air conditioners using thermodynamic analysis and multi-criteria decision-making tools. So here they almost used 12 to 14 refrigerants and analyzed based on the different criteria like improved thermophysical properties, and they have included safety measures, performance measures like cooling capacity, CO2 emission, and etc., and economic measures. All these included. From these figures from COP, TEVI, and lifetime cost, you can see from that, according to the COP, the refrigerant mixture R444B is found to be the good one. And similarly for the life cost. But on the other hand, if you see for the TEVI, R161 emits less emission as compared to all other refrigerants. But interestingly, if we consider all the these 5 measures shown in the table 3, after decision-making criteria, it lists R290 as the best one. In follow-up study, the same R290 refrigerant was studied in the same system where previously R22 was filled. In this work, they analyzed performance, emission, and cost-benefit analysis also. This is a system bench level studied in a well-developed and well-accepted psychrometric room. And they tested for different indoor and outdoor conditions which reflects low load, high capacity, low capacity around different atmospheric conditions. So according to all these conditions, we can see that cooling performance of 290 is slightly lower than R22. But on the other hand, it has really good COP. It's about 7% higher. This is majorly because the system, like when we are retrofitting R22 with R290, this refrigerant liquid density is much better than that one, and so the refrigerant charge is almost 50%, half of the R22, and also it consumes less power. So because of less power consumption, it showed better COP. But similarly for TEVI analysis also, in TEVI analysis, there are 2 categories. One is direct and indirect, like one emission caused by the compressor power consumption from the grids, and another one CO2 emission caused by the refrigerant usages, refrigerant leakages from the system. So this indicates 16% decline in the TEVI. So both these studies showed that R290 is much better in retrofitting applications. And in this study also introduced same R290 refrigerant as a replacement for R420 and a slightly bigger systems like up to 10 kilowatt capacity system they introduced. And this system also showed a good performance in high capacities as compared to the 5.2 kilowatt system. We can see from this, the test result showed in the upper table. And also it had 14 to 34% reduced LCCP and TEVI. So all these studies suggested that we can use R290 in room air conditioning applications successfully. But the major problem is its flammability. To mitigate this flammability issue in automobile air conditionings, they used a secondary loop arrangements like they will not supply the high flammability refrigerant propane into the passenger compartment. Instead, they used an additional loop with a brine solution to the compartment. But in this kind of this kind of split air conditioners, we need to supply the refrigerant directly into the evaporator, which was placed in the room. So many protocols have been introduced to reduce the flammability issues by minimizing the refrigerant charge. So according to the new protocol, new standards, IEC standards, they set a maximum limit of 0.988 kilograms of CO2, sorry, R290. Moreover, by using water-cooled condensers and high-efficient mini channel heat exchangers, including plate heat exchangers, which helps to reduce the overall system volume and directly reduce the refrigerant amount. So these are all the strategies is following to implement R290 in real building cooling air conditioners. And next, we can see some kind of case studies. They have implemented a different low GWP refrigerant in building cooling and applications. In this first study, which was conducted in Ghana, so they used a ductless R290 system with a capacity of 5.27 kilowatts, and they followed the same IEC 60355 standard with anti-static packaging arrangement for the compressors. And they compared the performance with R22 and as well as R410A. So we can see from this both the tables. First table indicates its performance and like thermal performances, and second table it's all about the cost, economic viability. We can see that use of R290 instead of baseline systems which filled with R410A and R22, it had better energy efficiency. Like we can see that its EER value is about 3.5 against 3 and 2.8 for 410A and 22 respectively. Similarly, it had almost 40% lesser TEV as compared to both the refrigerants. So this real case study also like confirmed the studies made using the test benches and theoretical analysis. Further, cost analysis also shows slightly better in terms of cost. We can see about like 1,000 to 2,000 USDs are lesser for R290 systems. In the second study, which was installed in a Euro tunnel between the France and UK. So the tunnel length is about 50.5 kilometers. Like it has total of 8 centrifugal chiller units, 4 which was placed on the European side, like France side, and another 4 was fixed on the UK side. Each system has like 2,000 TR capacities, and they have installed like replaced R22 system with HFO R1233 which belongs to hydrofluoroolefin. So this study like indicates that roughly after first trial or first seasonal run, it roughly like 40% more efficient than the old one, and also has a COP level of about 5.76, which was previously about only 3.5 for R22, and also it only emits 750 metric ton of CO2 equivalent CO2 emissions. And the official data of Eurotunnel demonstrates an energy saving of maximum of 32% as compared to the old one. So it almost saved 4.8 gigawatt hour. But the problem with this particular HFO refrigerant is its TFA formation when it was released into the ambient. Because of an updated Euro protocols, this refrigerant might be banned in near future. Maybe they need to look for another better environmental friendly refrigerant. In another study, like another HFO mixture was used in a centrifugal chiller for a casino in UK. This casino has almost like 150 rooms, and they installed in an underground facility. They found it's about 20% of CO2 emission, sorry, COP as compared to R22, and also has only 250 kg of refrigerant inventory, while it was about 460 kg for R22. The specific advancement in this kind of facility, what they developed is they used an variable frequency dive controlled centrifugal chiller to enhance the part load efficiency and demand cooling controls. However, this refrigerant also has a TFA issue. More importantly, this refrigerant is classified under B1. B1 means toxic, like no flammability, but toxic, highly toxic. So there should be a proper ventilation. But in this case study, they have not provided the details about the chiller room ventilations. And in the last one, they used an ammonia. Everybody knows that ammonia is also has very toxic issue. So for this purpose, what they did is they used an indirect cooling, like they used a centrifugal chiller, which was fixed on the top of the building. And the total capacity of single chiller is about 60 kilowatts. It was fixed in the Logan City of Australia. So with this study, they introduced a new additional ventilation fan in the chiller room. This was helped to reduce the ammonia concentration within the room of less than 7,000 ppm, because ammonia is highly toxic. So it is not recommended to stay a person when it was leaking. And the installed capacity is about, we can see it's about 252 watts of compressor, and they used two kind of system. One is an air cooled system and another one is a water cooled system. So both the systems really performed well as compared to the earlier one, and it showed an improvement in COP from 2.52% to 3.83%, and also saves, because of less power consumption and improved cooling efficiency, it saved about 1,40,000 USD yearly. But the one criteria is we need to use an additional ventilation with good rate to reduce the ammonia concentration within the area of cooling. So overall, from all these results, we can see that there will be no perfect refrigerant exist. So like we can see from the basic HFO refrigerants are ultra low GWP, slightly inferior performance, but okay to retrofit based on the environmental concerns. But it has a TFA formation issue. It will affect the water bodies because of acidic rain. On the other hand, we can see ammonia is excellent in thermal performance with superior cooling and COP, but it is highly toxic. Similarly, R290 is also has excellent thermal performance, but it is highly flammable. So the focus is now should be given on to the safety of the occupants and the environment rather than the performance, because all these refrigerants are good in performance. So we need to focus on occupants and environment. Hence, the major move of low GWP refrigerant is towards R290 and R717. So this alternate refrigerant studies clearly indicates we can use low GWP refrigerants, even natural refrigerants, but we need to take care of safety. So this is one part, refrigerant. In beyond the refrigerant, there is another part. Like I already told, right? Emission due to the refrigerant usage is one. Another one emission is due to the power consumption. So we can also able to reduce the building cooling energy consumption through enhancing the system performance with the help of waste recovery technologies. So this kind of technologies, like most usefully, the more cooling energy from the air conditioners will be lost by the return airs and heating energy from the condenser, and also even the condensate water, which also has like 10 to 15% of cold energy of the total system. So if we recover these waste heats and used it for preheating and pre-cooling application. From that point, we can able to reduce the overall energy consumption and operational cost of the complete building. And also it can able to support low carbon building goals and can able to obtain green certifications. So these are all the waste heat recovery technologies. We can see that regenerative ventilation wheels, condensate waste heat recovery, and modification in air conditioning system cycle itself. And the last and efficient one is a thermal energy storage integration with HVAC systems. So some in this first regenerative will, usually what we will do is the return air from the room, which will be used to pre-cool the supply air. For an example, if return air is moving on the 27 degrees Celsius, but ambient is 32 degrees Celsius, if the 32 degrees Celsius ambient air interact with the return air, and that temperature will be reduced by 2 to 3 degrees Celsius. So which helps to reduce the evaporator load and reduces the power consumption. And the second category, condensate water recovery. Usually the condensate water temperature itself, it might be around 10 to 15 degrees Celsius, almost equal to the dew point temperature of the air. So like the amount of water produced, it has like same around 15% of total cooling load of the unit. So if we recover this condensate water, we can able to again pre-cool the air, or if it is a big capacity system, we can use the complete condensate recovery for cooling purpose of a small room in the same buildings. And additionally, this condensate water can be used for irrigation purposes also. And the next one, modified vapor compression cycle using HVAC. Here, what they did, this cycle, what it helps to is reuse of the waste energy within the refrigerant to preheat the refrigerant before the compressor inlet. With this kind of technology also, we can able to increase the performance of like a system COP significantly. And nowadays, this kind of internal heat exchangers are already equipped with all kind of VCR cycles. And the last one is thermal energy storage technology. So this thermal energy storage technology is used to reduce the overall capacity of the system and store the available energy when it is not used for the purpose, and it will be supplemented during the peak load conditions. So with this kind of technology, we can able to reduce the overall capacity of the system and also improve the energy efficiency. Some research studies on the energy recovery performance. So as I told, this study, you can see this figure, and this is an elaborated one. The condensate collection was used for the two purposes. One is like you can see from this diagram, that this condensate recovery will be used for pre-cooling the exhaust air, and also the supply air. So with this, both the concept and the same condensate water can be used to supply to the cooling towers. During cooling tower operations, there will be an always evaporation losses. So there should be always standby water supply. So in that point of view also, we can use this condensate water to the cooling tower and reduces the external water source consumptions. And you can see there are four different categories. See, in the first case, baseline and only condensate. So it can able to save 41% of water resources. And with that energy recovery, you can able to reduce, like after pre-cooling purpose, you can able to reduce 4%. And both energy recovery and condensate. And the last one is condensate, pre-cooling and energy recovery. So overall, you can see that the total energy of the system will be reduced significantly by 13%, and also you can use the same water to the cooling tower purposes also. It will save water resources by 37%. So it is clearly visible that using of condensate water can be used to enhance the performance and also reduce the external water sources. And this is a system like a split air conditioner system. They used an internal heat exchanger here to exchange the hot, like we can say they exchange the hot liquid refrigerant heat source to the cold vapor refrigerant coming out from the evaporator. With this, we can able to improve the cooling performance and also like avoid the liquid entry into the compressor. So it has both benefits. With this kind of system, like system 1 indicates the suction line heat exchanger with R22, and system 2 indicates suction line heat exchanger with R290. You can see that the total energy saving was up to 27% for the both system. With that, you can able to improve the efficiency by nearly 40%. But this improvement is based on the conditions only, specific conditions only. This will be vary sometimes. There will be a chances of too much of superheating at the compressor inlet, which might increase the compressor load more significantly. Because of increased superheat, there will be a chances of reducing the refrigerant flow rate throughout the system, which in turn affects the overall cooling capacity. So this kind of selection should be more careful, and the performance is not similar under the all conditions. And the last one is like the integrated PCM based tests, salt hydrate based PCMs, and used in the variable volume air conditioning system for reducing the overall energy consumption and system capacity. You can see from this figure, this is for summer and winter conditions. You can see the peak load of the unit is around from 11 to 2. So similarly for winter conditions also. So the purpose is to reduce this peak load demands. So with this, they introduced a test to store the available energy when it was not used for the cooling purpose in the spaces. So it will store that cooled energy by the PCM itself, and then that stored cold energy will be delivered during the peak time. You can see from this diagram, this is the test output, and you can see there is a sudden drop because until this point and this point the cold energy was stored, and you can see from 8 AM onwards there is a sudden increase in the peak load. So this peak load is supplemented by the energy stored by the PCM in the test. So with this, you can able to almost save much energy as compared to the other systems. This kind of systems are really available in many places. Even in Chennai also, it was available long back. They installed water-based tests along with in integration with the air conditioners. Some case studies on test integration and condensate recovery in the building coolings. So this is in India's first distinct cooling system at the Gujarat Tech City. You can see this building. It has total of 3 sections. One is central cooling plant, and the second one is chilled water distribution from the central cooling plant to the buildings, and third one is energy transfer sections. So this system actually based on the calculation of the area, actually it need about 270,000 TRs and requires 240 megawatts of energy for air conditioners. But what they did is they installed only 180,000 TR capacity for cooling that complete locality, and they installed tests for supplying up 60,000 TRs. Okay, so here a stratified based thermal energy storage tank was used, and which was charged during the off time and discharged during the peak time. So with this, again, the system capacity from 180,000 to 150,000 got reduced, and electrical demand also reduced to 135 megawatt as compared to the 240. So this was successfully installed in the Gujarat. And the second one is in Chennai. Metro Rail Corporations, what they did is they installed in their building, they have 43 air handling units and 29 ceiling suspended units for providing an air conditioning and effective cooling across all the floors and critical rooms. And the total capacity is about 1,750 TRs. In this 1,750 TR capacity unit, about 10,000 liters of water was produced from the condensate every day. So what they did is, this 10,000 liters of water capacity they have used for other purposes in buildings. With that, they can able to save 25% of the total building water consumption, and also saves around 6 lakhs rupees per year for the additional water charges. And the last one is, so first one is emission due to the refrigerant, which was reduced by using low GWP alternatives, and the second one is through integrating various energy efficient technologies and able to save the energy consumption of the system. And the last one is integration with the renewable energy power sources. So without this, all the energies came from the grids. So that is the major contributor for the emissions. So now the additional integration of renewable power sources might reduce the direct supply from the grid sources. So there are 3 different kind of cooling technologies have been already used, like solar photovoltaic plus conventional HVAC system, then solar thermal cooling plus absorption based chiller systems, and third one is a hybrid solar PV and thermal cooling with HVAC systems. So these are all the common 3 categories were available for the system. So with this concept, we can able to support net zero building certifications and cuts the electrical bill and peak demand charges, and overall reduces the carbon footprints from the system. So these are all the 3 3 schematic representation of PV plus conventional cooling and solar thermal plus absorption chiller and hybrid systems we can see. So many studies like theoretical analysis and test bench analysis have successfully proved, especially for heat pump application, they really proved. And in Anna University, they a small milk cooler was developed with the support of 2 150-watt panels. With that, they inbuiltly developed that used an water-based chiller unit for milk cooling purposes. It was also successfully run throughout the summer season, except the monsoon and winters. There is a need for a grid supply because of insufficient solar isolations. So the major problem with this kind of technology is available sources from the solar, because it is always flexible. It is not even it's stable. So this kind of technology can be used to reduce the energy sources, not by completely, maybe somewhat, some percentage from the conventional sources. For an example, there is a case study is there, like about 100 TR solar air conditioning system was installed in the Kailas Cancer Hospital and Research Center in Gujarat. They used solar concentrators combined with vapor absorption based refrigeration system. This vapor absorption was run by the biomass energy. The total capacity of this lithium bromide based VAR system is 600 TR, out of which 100 TR was supported by the solar thermal systems. We can see this. This is the aerial view of the solar panel, solar collectors areas. Like totally 100 concentrators have been used with a total area of 12.5 meters square. Totally 3 rows with 15 pairs were used, and 4th row has only the 5 pairs. So the total collector area is about 1,250 meters squares. So with this energy, what they did is they reduced the necessity of woods about 1,000 kgs daily. So this is also effective in reducing the emission from the biomass burning. So overall, this, once again. So overall, the coupling of low GWP refrigerants with renewable power sources represents most sustainable pathway for the future. So the final takeaway from this session is the transition to eco-friendly refrigerant and sustainable cooling is not an option, it is an essential for the future. And key taken points are use of low GWP refrigerants such as R290, R717 and HFOs offers feasible pathways, though each has certain limitations. And international protocols and Indian policies are driving this transition perfectly. And case studies worldwide clearly demonstrated the technical and economical viability of eco-friendly refrigerants, and efficiencies was significantly improved through waste heat recovery and test technologies. Further reduction can be easily obtained using renewable energy integration. So the final message is the building sector must transition towards sustainable cooling as a cornerstone of climate conscious developments. So herewith I conclude my session. I thank you all for your attentions and active participations. The subject of eco-friendly refrigerant is not only an engineering challenge but also a societal necessity. So now I welcome questions from the audience side.
Thank you, Professor. Now I request the participants to figure out their questions. They can unmute and then ask the questions. Otherwise, they can put their questions in the chat box. Professor, what is the most promising refrigerant which is commercially available in the market?
Like already R290 is commercially available for small capacity systems, and if we go for bigger like complete buildings with the distinct coolings, we can use like ammonia, because it will not directly feed it into the room. So instead it will cool the brine solution. That brine solution will only come to the cooling spaces.
Any other questions from the participant side, please? Questions are welcome. You want to have an active interaction for another 10 to 15 minutes. So what is the research trend in this particular area, your region, sir? I mean in Korea.
Yeah, so actually
So
we are
Yeah.
driving with R290, and we are trying to use plate heat exchangers. Like instead of conventional in water cooled systems, we try to use advanced offset pin type plate heat exchangers, which helps to reduce the system volume. So with that, you can able to get good performance despite it has pressure loss issues, but we can get good performance and also reduce the refrigerant inventory as much as possible. So the main target is to reduce the refrigerant inventory in the system, because 290 is flammable one. And recently, like IEC standards also might have some liberal things, like they increased the limits. Initially, it was about 360 grams, and now it was slightly increased. And the focus is shifted towards the safety aspects.
What is the kind of refrigerant which is under R&D? It should be an alternative for the
No,
R290.
presently, like R290 is already implemented.
Yeah.
In
So
many
what
places.
I mean,
Now
what would be the probable,
like now that's what I'm saying. Now the target is to analyze the worst case scenarios to avoid the flammability issues. And like integration of like solar systems, because for that we needed DC compressors. So DC compressors are nowadays too much of cost as compared to the conventional ones. So and also it has some other issues like it like sometimes it will not run directly because of insufficient isolation. So now they plan to use some test integrated technologies, and also like RPS controls, like regulated power supply controls they have implemented. So the this kind of technologies are now they are doing. Specifically, the focus is on to improve the energy efficiency of R290 systems using multiple techniques.
okay. So
And
we
even
have a question in
like
chat
like
box.
machine learning, like IoT based controls are increasingly a lot nowadays to ensure the safety also and efficient running of the system.
By implementing the machine learning, Professor,
Yeah.
what scenario it will handle? What kind of scenarios will be handled by the machine learning?
No, the thing is like for this smooth running and to identify the like accidental scenarios much earlier. That is the major thing. So
And
with
what
that
are
help,
what
we can like exactly I don't know what kind of tools their algorithm they are using, but the major concept is this one.
okay, and under what circumstances this R20 will become flammable for this?
Like it's like there like when it released into the room. For an example, it released from the evaporator, which was fixed on the like it's somewhat like 10 feet high on the wall, right? If you consider as a split air conditioner, okay. So it is like based on the two criteria. So because it's a low temperature one, okay, so it will not have high temperature to ignite itself. So if there will be any electrical spark within the room, one thing. And second one, the leak spreading is based on the blower running. If the system was running, that time it leak happens means the spread will be much more faster as compared to when the system was in off condition. So this is the scenario nowadays they are analyzing it. So if it released within the like condenser side means like there will be no direct damage to the occupants, but complete burst will be happen because of sparking. So that is why even anti-static current spark packages they have recommended for R290 for avoiding those kind of scenarios in outdoor units.
Okay. We have a question in our chat box, Professor. Professor Parani is asking, during the night, the environment temperature may be less. We store it in PCM, then it may improve COP of refrigeration system and cooling system. Is there any system to adopt this in India?
Yeah, it is there. The same thing I already told you, right? In Gujarat, same kind of system, but instead of a solo system, it was a big one, distinct cooling system. The same technology they are using. Even in, I think, in Chennai Tidal Park also the same kind of system is there. They used to spherical capsule based. They filled the PCMs in the spherical capsules, various spherical capsules in the test tank. They also implemented that one long back. Even in foreigns also many places they are utilizing. Especially like for an example, if you have what's that?
Not much explored, I'm very Professor. It's not much
still
explored.
It is there. Still it is there, but like how can I say, the maintenance and somewhat initial cost might be high. Like you need to add, but add one separate circuit for this. But the benefit is the total capacity of the system you can be reduced. For an example, if you want 180 TR, for an example, okay, for a peak load. So usually the system will be designed based on the peak load, right? So if that peak load will be available only for 2 to 3 hours in a whole day, but the system is always run for that peak load. So in that point, there will be an energy loss. When system runs on the partial load, there will be an energy loss, right? So what they will do is they will reduce the total system capacity from 180 TR to 100 or 150 TR. That system will run throughout the day. Okay, during night times, it will also run. That time, the cooling energy shifted towards the test. So there, that cold energy will be stored. And then when system was needed, like at the midday, we need a peak load. So that time, what system will deliver only the 100 TR. Remaining 80 TR will be delivered by that stored energy from the PCM. So with that category, you can able to reduce the energy consumption also, because system will not run partially.
Yeah, sorry for interfering. That major part can be obtained from PCM purchase. Is it so?
Not major part, only by maximum 20 to 30%, not whole system capacity.
Yeah. What kind of PCM commercially they are using, Professor, in those systems?
Salt, exactly, I don't know, but in that, I think salt hydrates they used, and in one plant in ITC they used, I think, water. I think like water or water. I don't know exactly. Even water is also has a really good thermophysical properties and high latent heat. But the problem is it has very high subcooling nature. So that is the only thing the water has. But for that, they have added some nucleating agents to reduce that one. If with water with nucleating agent, it might be a good one.
Okay. But it is having less energy density only water compared to other PCMs.
Yes, and also it has another problem, like how can I say, that volume change is also much high. So there will be a question on the next capsule's integrity. That is also there.
Yeah.
In some other one, I don't know the exact composition, but salt hydrates they used.
Okay. So only now the commercial systems, the salt hydrates are under what is predominantly used. Am I right, Professor?
Yes, with some nucleating agents.
What kind of nucleating agents?
Sometimes they will not reveal from these case studies.
Okay.
I don't know exactly, but many papers have been published with a different kind of like SDBS. One more thing, Pseudomonas and.
Yes, sir. Good evening.
I don't know. I forgot that.
Sir, sorry for disturbance.
Chandrasekhar, sir.
Yes, sir.
Please,
sir, myself also used to water as in the spherical capsule. So I used to Pseudomonas fluorescent as nucleating agent.
Okay, sir.
And it completely eliminates subcooling. Even I conducted experiment at -2 degrees. Am I audible?
-2 degrees. Okay. Yes, sir.
-2 and -6 degrees, I have conducted keep the surrounding bath temperature and found solidification occurs without any subcooling.
Okay, fine, sir. How much volume percentage you can state, sir?
Pardon, sir?
So how much volume percentage you used, or mass percentage of?
Well, I filled 90% volume.
No, that's fine. In a spherical capsule, we usually fill 90 to 95%. That I agree. For that 90% of volume, how much mass of nucleatic agent you have used?
Mass of nucleatic 0.18%.
Yeah, 0.1.
0.18% of the.
If you add more, it will affect its energy storage properties.
Yeah, 0.18%.
Yeah.
0.18%. That is around 1/1000 of mass.
Yeah, I understood, sir.
1/1000 mass. So it completely eliminates subcooling. And similarly, I also use the effect of fill volume. If you fill 95% fill volume, subcooling is completely eliminated, not at -2, at -6 for my spherical capsule.
Okay.
Fill volume also
but that fill volume, it depends on the different PCMs, right?
No, sir. No, correct.
Only for water, you're saying. Okay.
For water during solidification, 8.8% will get expand. 8%.
Okay. 8%.
So at least you have to keep 92%. So
92%, yes.
Generally, because since we are measuring through thermocouple, so I prefer 90% initially. Then after change up to 95%. So and also refer the literature. So the conductor experiment from 80% fill volume. So I calculated all fill volume, and I find that at 80% large amount of subcooling, and 90% fill volume no subcooling.
Okay, sir. Because the subcooling is the major problem with the water. If we eliminate that one, even we might no need nanoparticles, because nanoparticles, it does not have long-term stability, and nobody tried exactly. Only for paper purposes we can do with nano, but real application it is really hard. But with nucleating agent is much better.
Yeah, correct, sir. So that was very low limit. That is 1 by 1 part of 1,000 part of PCM. 0.1 weight.
Have you tried with different capsules or only with spherical?
So only spherical capsule of LDP, as well as I conducted with the stainless steel capsule for larger diameter, around 100 centimeter diameter, 100 mm diameter. I used spherical stainless steel spherical capsule.
Okay, sir. Thank you. Thank you for sharing your information.
Yeah. Okay, sir. Thank you.
Thank you so much.
And also one more point, that is when compared to paraffin, water has energy density almost twice of paraffin.
Yes, because it has much higher thermal conductivity, latent heat.
Correct. Similarly, thermal conductivity also much higher than paraffin, almost 3 times in the liquid state, and around similarly the solid state of water, still it is higher. That is around 2.2 watt per meter Kelvin.
Okay, sir. Fine. So, have you analyzed any leakage analyses or corrosion related studies with water and nuclear?
No, sir. I did. Actually, my studies only with one single capsule.
Yeah,
and I analyzed
I also did many with single capsule.
With kindly look at my article. I mean, I have found many first time reported findings.
You're from SRM, sir?
Yeah, SRM. Yeah, SRM. Yes, I am the classmate of former VC.
Yes, sir. I know, sir. I have seen you. I think I also did PhD and masters in CNG.
That's also look at your face. I also recalling where I was.
Yes, sir. I think we met for the data logger. I think.
Might be, sir.
Yes, sir.
Thank you.
Thank you so much for your valuable sharing, sir.
Thank you, sir. Thank you.
Any other question from the participant side? Any questions? We appreciate the interaction. Sir, recently I heard the coconut oil can also be used as a PCM, sir.
Yes, sir. We tried actually. One of our article is in under revision in energy storage. We studied in the same way what Professor Chandrasekhar told. Like we also analyzed its freezing behavior in spherical capsule, which is made up of LDPE. But what we did is it also has subcooling issues around 2 to 3 degrees Celsius. And for that, we used same coconut oil byproducts, like an activated carbon, which was derived from coconut cells. So for circular economy, we tried that PCMs, and many studies they have did only for pre-cooling applications. Like some studies they did like with condensate recovery for the cold energy from the condensate has been recovered and stored in the spherical capsules, which was filled using coconut. That stored energy was used for pre-cooling of small refrigerator applications, like pre-cooling of apple, potatoes, and like that they used.
Okay.
And even for like PCM panels, coconut oil based PCM panels have been installed in the cars in like I don't know where they did, maybe Oman or UAE, I don't know exactly. They also tried coconut oil.
What about the results, sir? Is it
sir, like we never compared with the water, but we tried only for recovering the condensate. Like we fixed about the same like 10 to 15 degrees Celsius of source, because it will start to solidify and melt around 22 to 24 degrees Celsius. Like based on the coconut oil nature, like based on the source, the nature will be vary, right? So its chemical composition will be vary. So based on that, we tried, we like procured it from the local market, that coconut oil from in Gangayam, and we tried that study. It shows some promising results.
Okay. What kind of PCM is in trend, sir, right now? Yes, we have tried a lot with wax. We tried a lot with
no,
salt
actually,
hydrates.
from like, how can I say? From my point of view, we need to go for eco-friendly options. That's why we tried even some kind of gels, even from aloe vera gel, that can be also used as a for either as a, you can use it as a PCM, and also you can use it as instead of a thickening agents, you can use aloe vera. It will increase the, for an example, if you mix with the water, it will increase its thickness. Like the density will be increased. It will connect the water molecules and it will act in between that. So it might help to reduce, from my point of view, it might help to reduce cooling also.
Yes, sir. We have a question in chat box.
Yeah.
Professor Jinka Srirangan Aikadu asked, freon gas are harmful to atmosphere. How they can be eco-friendly?
No, we never recommended freon gases, right? I already told, freon gases is not good for environment. That's why we tried to shift towards R290 and ammonia 717. So freon gases were almost banned everywhere. You can see R12, it was banned long back. Now HCFC 22 also already banned, started banning. In 2030, like already that step-by-step reduction started in India. Around 2040, it will be completely banned. So nobody will refer freon.
Right. So however, we need answer from your answer. That's like,
So
I hope Professor got the answer. As I told, freon is completely banned right now. Yeah, so we are moving further forward with CFC-free gases. Now all we are having using only the refrigerators and the air conditioners which uses only the gases which are free from CFC.
Even 32 also they used it. It also halogenated refrigerant, but still they are using. The reason is its GWP is lower than other freon gases. But the problem with like 32, it is also mildly flammable category. That's why I told there will be no perfect refrigerant. There is no perfect refrigerant. You need to balance all the things. Performance, which trade-off you need. Like what kind of trade-off you need to make. For an example, trade-offing between the performance, safety, and environmental concerns. These all three need to be taken care. For an example, if you go for like a room air conditioner instead of distinct cooling, in room air conditioner you can try R290, but with more safety concerns. You need to reduce its charge, and you need some safety precautions. But if you go for bigger systems like distinct cooling, you can use ammonia chillers. Only the brine solution will come from the chiller you plan to the cooling area. So that kind of trend also we can use.
Any other questions?
Sir, good evening, sir.
Good
Sir, good evening, sir.
Good evening.
Sir, what about the graphene based nanofluids, graphene oxide, something like that? Can we use for solar collectors or solar cells?
Yeah, actually, like how can I say, it will be it's as a cell material or just for coating purpose? For which purpose you are asking?
Coating, sir.
Like with PCMs, right?
Yeah, yes.
So these kind of technologies you can use only for test bench level. You can't use like you know that there will be an always agglomeration with nano, and even with PCMs, if you do not have perfect capsulation, like there will be a phase segregation when it started to melt specifically. So if you, for an example, if you are using in a solar, in a solar concentrator, which may be around 30% to 30 degree or 40 degree slope, for an example, based on its density, it will come down. So for that, you need a perfect design inside to avoid these kind of segregations. And with nano, for an example, if it is a flowing liquid is fine, because somehow that flow will help to remix with the fluid. But if it is a stationary like PCM, it surely will settle down after a certain period. Everybody knows that one, but that initial performance enhancement was much better. For example, with graphene, it's really good, and you can go for magazine also. It is specifically good in high temperature applications, but it's long-term stability, that is the real question mark.
Yes, sir. Regarding the use of nanoparticles, as of now, we are having a problem with agglomeration and
yes, sir.
precipitation. Yeah.
We can study. We are even if you take simple like DSC analysis, a sample without freezing melt treat after treat, it will be very. We did with coconut oil. It showed double peak. It initiated at some point and ended at some point. For an example, 22 degrees and minus 10 degrees if it is ending for freezing. But after this is fresh sample. After treated sample, we tried the same, but it how can I say, there will be a little difference in enthalpy, but huge difference in initiation point and end point. So that we don't know, right? But really, we need to test with those samples. The tested samples only we need to test.
Yeah, for the longer cycle period, it is not reliable.
Yes, sir.
So
Sure. It is not
That
reliable.
is
Even like coconut oil itself,
substitution.
even coconut oil and some other natural oils also, because of its oxidative nature, that also we need to take care. And like system integrity in terms of corrosion analysis, that also we need to check.
So I hope that is what the major challenge with using nanoparticles in the fluids and all, and along with also with the PCM.
Yes, sir. Yes, sir.
Becomes a greater challenge to make it commercial.
Yeah,
Because
yes,
during the R&D level, some few tests gives some promising result. But when we go for a longer period of operation, definitely there is a precipitation.
Yes. Sure.
Any other questions from the participants? If no more questions, we can wind up the session. And we'll move forward to the next session.
Okay, thank you so much.
There was one more question. It is now
Yes,
out of
yes,
what
sure,
discussed
sir.
here. In South Korea, what is the, if somebody wants to move there for career perspective or for doing some postdoc, what is the procedure, Professor? What are all the hot topics they are dealing now?
Like hot topic means specifically in my field, what we are doing is in vapor compression cycle, we are developing with CO2, because we mostly in present we mostly working towards automobile sector. So what we proposed is propane and CO2, not ammonia. Ammonia is indirect cooling, which will be used in conventional commercial systems, but in automobiles, our target is 744, CO2, and 290. Now we are using that integrated thermal management systems in vehicles. Like that unit will be used for multi-purpose, like cooling of cabin or heating of cabin, preheating of battery under cold climate, and cooling of batteries under conventional heating climates. And some other things for drive motors cooling also. So the combined one. Now, for this combined technology, what we are using is, instead of conventional vapor compression with IHX, now we are developing vapor injection technology. It is already developed one, but commercially not available. So that vapor injection technologies, we are now developing a system level bench study here for automobiles, for passenger cars.
Okay. It's an integrated conditioning system. Which can be
Integrated
useful for
thermal management
all the
system.
Yeah. So what the South Korea, the Korean universities are looking for somebody's
Sir, like basic criteria is at what topic you researched and how many papers you have. This is the basic one. And if you need a good job, like a good postdoc jobs, you can try for brain pool fellowship. It will give like good salary, one thing, and also it's a prestigious one in Korea. You can try yearly. They will call for. You have to approach a professor and you need to submit a proposal with that. So if that one selected, you can come here with that fellowship. Otherwise, as usual, based on the websites checking on LinkedIn.
Okay. So
we
the
can
better
find.
one is brain pool fellowship.
Yes, sir. Brain pool you can try, sir. This is for those who completed PhD. For doing PhD also much easier here. Like there are two ways. One is direct approaching with English score, and another one is you need to clear the Korean exams. With Korean fellowship you can come. Korean language fellowship you can join here. These are the two ways.
Okay, professor.
But from our field, somewhat less persons. From the thermal field, somewhat less persons here. But usually physics, chemistries, and those who are working in materials and biomedical applications, they are the huge numbers of Indians.
That's good to hear.
Yes.
And what area they are majorly focusing on, professor? Either they are working on a theoretical part or experimental
Sir,
part?
here they will, as I said, they will check even for supercapacitors. They are working in many places. They will develop a small test bench level. With that, they will only characterization itself. They will finish their work. Only characterization. Like only with the help of CV analysis, they will do.
That is enough.
That exactly I don't know, but most of the persons in my circles, they are doing this, and some other persons are working in biosensors also with different kind of materials.
So as far as your words, you can understand that there is a
but
huge scope for the person with good thermal background.
Yes, sir. Obviously, sir. Thermal field, especially for building cooling and refrigerants, huge scope, sir. In Europe side also we can go for nowadays. Like 10 years back, most of the European countries, they have implemented HFO based refrigerants. Now due to the PFAS regulations, they are moving to the CO2 also because of its climate. So they need heating. But in our country, we need cooling. Yeah, this is the problem.
Yeah. Okay, professor. Thank you.
Sir.
Thank you so much.
Thank you so much for giving this wonderful opportunity.
Presenting a wonderful presentation over here. It was really a great time we had here with you, and I hope the participants have really enjoyed the session. And definitely will come back to you in future also regarding the sessions and other collaborations also, professor.
Sure, sir.
Be in touch with us. On behalf of the Department of Mechanical Engineering, Adishankara Deemed University, and on my own behalf, on behalf of all the participants, I once again thank you for being here and presenting a wonderful presentation, professor. Thank you so much.
Thank you so much, sir. Thank you all. See you, sir.
Thank you, sir. See you. Dear participants, thank you for your patience. Still, we have a very less number of people joined here. And again, I am emphasizing regarding the attendance. For getting the certificate, actually, it is the certificate you can get through your ATAL login, which requires minimum 80% of attendance and minimum 70% of mark in the assessment test that we are going to conduct today. And you have to fill your final feedback in your login. So these things are required to get your certificate. So your attendance is very much important. Okay, and this recorded session has to be sent to the ATAL also. So we cannot give the attendance just like that. So please be with us, join, and show your virtual